Hey fellow nerds, today we will solve gate problems on OpAmp circuits from 2015 to 2016. Let us take the first question. We have an ideal OpAmp. It has voltage sources V1, V3, V5 up to Vn-1 connected to the non-inverting input and V2, V4, V6 up to Vn connected to the inverting input. It is given in the figure over here. Plus VCC is 15 volt, minus VCC is minus 15 volt. The voltages V1, V2, V3 up to Vn are 1 minus 1 by 2, 1 by 3, minus 1 by 4, etc. What we have to find out is the value of the output voltage as n approaches infinity. We'll start by calling this point A and this point B. Let us apply Kirchhoff's current law at node A. There will be a current flowing through this 1 kilo ohm. According to Ohm's law, it will be VA minus V1 divided by 1 kilo. The next current will flow through this 1 kilo ohm resistor and its value will be VA minus V3 divided by 1 kilo. There will be n by 2 such terms, the last one being VA minus Vn minus 1 divided by 1 kilo. Along with all these, there will be one more current, the one that flows through this resistor. And its value will be VA minus 0 divided by 1 kilo. According to the law, the sum of all these currents should be equal to 0. We have 1k in the denominator of all these terms, so we can just cancel it. Let us group all the VAs. There will be n by 2 VAs from all these terms, plus there is one more. So the total number of VAs in this equation is n by 2 plus 1. So if we take all the VAs together and take minus V1 minus V3 up to minus Vn minus 1 to the other side of the equation, this is what we get. Now let's take n by 2 plus 1 to the other side of the equation, so we have an expression for VA. Now let us apply KCL at node B. We can take the current through the 10 kilo ohm over here as the first current. According to Ohm's law, the value will be VB minus V2 divided by 10 kilo. The next current will be VB minus V4 divided by 10 kilo. There will be n by 2 such terms, the last one being VB minus Vn divided by 10 kilo. Along with all these, there will be one more current, the one that flows through this 10 kilo ohm resistor. And its value will be VB minus Vout divided by 10 kilo. According to the law, the sum of all these currents should be equal to 0. Now, since we have an ideal OpAmp, using virtual ground concept, we can say VA will be equal to VB. That means in this equation, we can replace all the VBs with VAs. Then the equation becomes like this. Again, there is 10k in the denominator of all these terms. Let us remove it. Let us now take VO to the other side of the equation. Now let's group the VAs on the left hand side of this equation. There will be n by 2 VAs plus another VA. Total number of VAs will again be n by 2 plus 1. Along with that, there is minus V2 minus V4 up to minus Vn. By doing this, we can write an expression for the output voltage VO. VO is n by 2 plus 1 VA minus V2 minus V4 up to minus Vn. But we have already found an expression for VA over here. Let's replace VA in this equation with that. Here we can cancel n by 2 plus 1 and n by 2 plus 1. Then the equation simply becomes V1 plus V3 plus up to Vn minus 1 minus V2 minus V4 up to minus Vn. Or we can group it like this: plus V1 minus V2 plus V3 minus V4 up to plus Vn minus 1 minus Vn. The values of all the voltages are given in the question. If we use them, the sum becomes like this: 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, and it goes up to infinite terms. Because what we have to find out is the output voltage when n approaches infinity. We have 1, 1 by 2, 1 by 3, 1 by 4 up to infinite terms like that. What we have is an infinite harmonic progression. Its sum never converges. Sum of an infinite harmonic progression is infinite. That means the output should be infinite. But it cannot be, because it is limited by the saturation voltages. Since the value here is positive, output will be limited at the positive saturation voltage, which according to the question is 15 volt. So the final answer is 15. We'll see the next problem. We have a signal Vi given over here. Its peak voltage is 8 volt. It is applied to the non-inverting terminal of an ideal op-amp. You can see that over here in the figure. Base emitter voltage of the transistor is 0.7 volt. Beta is 100. Potential drop required for the LED to switch on is 1.5 volt. VCC is 10 volt and minus VCC is minus 10 volt. We have to find out the number of times the LED glows. Before we do the math, I want to explain to you how this works. We have a transistor over here. It needs 0.7 volt across the base emitter junction for it to be switched on. Emitter is at 0 potential. That means base has to have 0.7 volt. Assume that we do have it. In that case, the transistor will be switched on, which means a collector current will flow like this, switching the LED on. So to switch the LED on, we need a positive voltage over here. That means the voltage here should also be positive. This is the output of the op-amp. Let us call it Vo. You can see that the op-amp does not have a feedback, which means output is always going to be saturated. It will always be either plus VCC or minus VCC. But we just said for the transistor to be switched on, Vo has to be positive. We need the output of the op-amp to be at the positive saturation voltage. When does that happen? When input which is given at the non-inverting terminal is greater than whatever potential we get at the inverting terminal. Potential at the inverting terminal is given through a voltage divider. We have a 10 volt. It is divided between 8 kilo ohm and 2 kilo ohm. Out of that, whatever is dropped across the 2 kilo ohm comes out over here. Let's call this potential VA. VA will be equal to 10 divided by 8K plus 2K multiplied by 2K, which is 2 volt. Now that means input has to be greater than 2 volt for the transistor to switch on. Let us now find the value of the base current. It is equal to the current flowing through the 15 kilo ohm resistor. The 15 kilo ohm resistor has the output on one of its ends. On the other end, it has VBE. That means the net potential drop across the 15 kilo ohm is Vo minus VBE. And that means current IB will be equal to Vo minus VBE divided by 15 kilo ohm. At this point, output is saturated at the positive saturation value. According to the question, it is 10 volt. VBE is 0.7 volt. Giving the values, we get the value of the base current. It is 0.62 milliampere. Now let us calculate the collector current from this. Collector current is beta times the base current. Beta, according to the question, is 100. That makes the collector current 62 milliampere. This is the current that flows through the 100 ohm. Using Ohm's law, we can find the potential drop across the 100 ohm. It is the current multiplied by the resistance and it comes out to be 6.2 volt. This means out of the 10 volts supplied, 6.2 will be dropped across the 100 ohm. What is left is 3.8 volt. The LED only needs 1.5 volt to glow, which means it will glow. So the condition for the LED to glow is that the input should go above 2 volt. Let us look at the input and see how many times that happens. 1, 2 and 3. Input exceeds 2 volt 3 times, which means the LED will glow 3 times. Let us see the next problem. We have a constant current source. It is shown in the figure over here. Beta represents the current gain of the transistor. What we have to find out is the load current IO through the resistor RL. Let's take the circuit. Let's call this node A. So the potential here will be VA. Let's call this node B. So the potential there will be VB. If we have VB here, then at this point also we'll have VB. Let's mark IO over here. Emitter current will flow like this over here. Let's call it IE and mark it over there. Collector current will flow over here. Let us mark that also. Clearly, the current through RL is equal to the collector current of the transistor. Assuming we have an ideal op-amp, applying virtual ground condition, we can say VA will be equal to VB. Now, we have VCC over here. Out of that, V reference will be dropped across the Zener diode. Whatever is left come out as VA. So we can write VA is VCC minus V reference. But this is equal to VB. Now let's find an expression for the current IE. IE is the current that flows through R. R has a potential VCC on one of its ends and VB on the other end. Using Ohm's law, current IE will be VCC minus VB divided by R. But VB is VCC minus V reference. Let's replace it. Now VCC and minus VCC gets cancelled. IE is simply V reference divided by R. What we want to find out is IO, but IO is equal to IC. IC is the collector current. It is related to the emitter current as alpha times IE. Alpha is beta divided by beta plus 1. And that gives us our final answer. Load current is beta by beta plus 1 multiplied by V reference by R. Option B is correct. We'll see the next problem. In the circuit given, the op-amp is ideal. Gain V out by V in is minus 12. We have to find the value of R in kilo ohm. Let us start by calling this point X. So the potential here will be Vx. Now let us apply Kirchhoff's current law at the inverting terminal. Since we have zero potential over here and the op-amp is ideal, here also we'll have zero potential. So this current will be V in minus 0 divided by 10 kilo ohm. All of this current will flow through this 10 kilo ohm. It has zero potential on one end and Vx on the other end. So this current will be 0 minus Vx divided by 10 kilo. According to the law, these two currents should be equal. 10k and 10k can be cancelled and that gives us V in is equal to negative of Vx. Let us now apply KCL at the point X. We have three currents. First, I will take the current that flows like this. Since this is the direction I am taking, the current will be Vx minus 0 divided by 10k. Current flowing through R can be taken like this. Its value will be Vx minus 0 divided by R. Current through the next 10 kilo ohm can be taken like this. And its value will be Vx minus Vo divided by 10 kilo. According to the law, the sum of these three should be equal to 0. We know Vx is negative of V in. Let us replace all the Vx's in this equation with minus V in. Now Vo by 10 can be taken to the other side of the equation and we can combine all the V in terms. That gives us this. 1 by 10 plus 1 by 10 will become 2 by 10. Let's take this 10 to the other side of the equation and finally write an expression for V out divided by V in. It will come out to be negative of 10 by R plus 2. But V out by V in is minus 12. Solving this, we get the value of R. It is 1 kilo ohm. Let us see the next problem. In the circuit given, op-amp is ideal. What we have to find out is the 3 dB cutoff frequency in Hertz. The trickiest part in this question is to figure out the RC network that is providing the 3 dB frequency. Once you do that, it is cakewalk. So let us start by taking the circuit. The capacitor has one end grounded. The 10 kilo ohm over here also has one end grounded. The first thing I am going to do is show the grounds separately like this. Take a look at this resistor over here. One of its ends is connected to the input terminal. We know no current can flow into the input terminal, which means no current is flowing through the 10 kilo ohm. And that means even if you remove it from the circuit will theoretically work the same. So let us remove it and make the circuit simpler. Now, do you see the RC network providing the cutoff frequency? Yes, it is this. R is 10 kilo ohm, C is 0.1 microfarad. Cutoff frequency is given by 1 by 2 pi RC. Giving all the values, it comes out to be 159.15 Hz. Let us see the next problem. We have a voltage regulator circuit. Input voltage is 20 volt plus or minus 20%. The regulated output voltage is 10 volt. OpAmp is supposed to be ideal. We have to find out the maximum power dissipation in the transistor Q1 for a load RL drawing 200 milliamperes of current. Let us start by marking some currents. The first one obviously is the current that flows through RL. It is 200 milliampere. We have 4 volt over here. Since the OpAmp is ideal, using virtual ground concept, we can say here also we'll have 4 volt. Then that means over here we get 4 volt. Now if you take a look at R2 has 4 volt over here and 0 volt over here. So the current that flows through it will be 4 divided by 10 kilo ohm, which is 0.4 milliampere. We know no current can flow into the input terminal. That means all of this current must have come through R1. Let us mark the current. Let us also mark the collector current IC over here and the emitter current IE over here. Ideally, IC will be approximately equal to IE. Now, if we apply KCL at this node, we can see that IE is coming into the node, 0.4 milliampere is going out of the node, 200 milliampere is also going out of the node. So, IE has to be 200 milliampere plus 0.4 milliampere and IC will be equal to that. What we have to find out is the maximum power dissipation in the transistor Q1. Power is the product of voltage across the transistor and the current through it. Voltage across the transistor is VCE and the current is IC. According to the question, output voltage is 10 volt, but output is taken from the emitter, which means this is equal to the emitter voltage. Input is 20 volt plus or minus 20%, but input is given to the collector. That means this is equal to the collector voltage. Since input is 20 plus or minus 20%, the maximum value of input will be 20 plus 20% of 20, which is 4, which gives us 24 volt. For maximum power dissipation, we need the maximum value of VCE. For that, we have to take the maximum value of VC and subtract VE from it. Maximum value of VC is the maximum value of input, that is 24 volt. VE is 10 volt. That gives us 14 volt. We already have the value of IC. All we have to do to get the maximum power dissipation is to take the product of these two and it comes out to be 2.8056 watt. Let's take the next problem. It is given that the OpAmp in the circuit is ideal. What we have to find out is the output voltage VO. Now in the first stance, this circuit looks like a non-inverting amplifier. Input is given at the non-inverting terminal along with the negative feedback. But here is the twist. This point over here is grounded. Taking a closer look, you can see that the 1 kilo ohm resistor is grounded on both sides. It has zero potential on both ends, which means no current will flow through it. We can even remove the resistor. The actual circuit may look like this. The inverting terminal is grounded, which means the potential at the inverting terminal is always going to be 0 volt, no matter what you have at the output. Listen carefully. Even if the output changes, the 2 kilo ohm resistor, which looks like a feedback resistor, will not be able to change the input at the non-inverting terminal. That means effectively there is no feedback. And that means the output is always going to be saturated. Here the input is positive and it is given to the non-inverting terminal. At the inverting terminal, we just have 0. So the differential input is 1 minus 0, which is positive. That means output will be the positive saturation voltage, 12 volt. In the next problem, we have a bistable circuit. OpAmp is ideal. Saturation level is plus or minus 5 volt. What we have to find out is the value of resistance R1 in kilo ohm that gives a hysteresis width of 500 millivolt. What we have over here is an inverting Schmidt trigger circuit. The upper threshold voltage is given by the expression negative R1 by R2 multiplied by negative Vsat. Here negative Vsat is minus 5 and R2 is 20 kilo. So we get this. The lower threshold voltage will be negative R1 by R2 multiplied by positive Vsat. Positive Vsat is plus 5. R2 is again 20 kilo. That gives us this. Hysteresis width is supposed to be 500 millivolt. It is the difference between the upper and lower threshold voltages. Let us substitute the values. The right hand side of the equation can be simplified like this. 2R1 divided by 20 kilo multiplied by 5. From here we can find the value of R1. It is 1 kilo ohm. Let us see the next question. We have a circuit. Output is VOA when switch is in position A and it is VoB when switch is in position B. The switch can be seen over here. Assuming the OpAmp is ideal, we have to find out the ratio of VoB to VOA. Let's consider the first case where the switch is in position A. This 1 kilo ohm resistor over here will get a voltage 1 volt. This one will not have anything. It is open on one end, no current will flow through it, so we can just remove it. The equivalent circuit will look like this. We have a 1 volt here. It will be divided between this 1 kilo ohm and this 1 kilo ohm. Out of that, whatever is dropped across this 1 kilo ohm is the potential that we get over here, and that goes to the non-inverting input. Since the resistances are equal, voltage will be divided equally and we will have 1 by 2 volt here. What we have is an adder subtractor. Gain for the inverting terminal is negative of R1 divided by R2. So the 5 volt will come out at the output as 5 multiplied by negative of 1 divided by 1. Gain for the positive terminal is 1 plus R1 by R2. So the 1 by 2 volt will come out at the output as 1 by 2 multiplied by 1 plus 1 by 1. So total output will be minus 5 plus 1 or minus 4 volt. Now let us try to find out VoB. For that, let us consider the switch is at position B. In this case, this 1 kilo ohm resistor will get 1 volt. This one will be open at one end, which means no current will flow through it. It's basically not doing anything. We can just remove it and the equivalent circuit will look like this. Now we have an inverting summer. Both inputs are given at the negative terminal. Gain for the 5 volt will be negative 1 by 1. Gain for the 1 volt will be negative 1 by 1. This is what we get at the output. It is minus 5 minus 1 or minus 6 volt. What we need is the ratio. It is 6 divided by 4 or 1.5. Let's take the next problem. We have a circuit. OpAmp is ideal. What we have to find out is the bridge output voltage VO in millivolt for the value of delta being 0.05. VO is the potential between these 2 points. It is given that the OpAmp is ideal, which means we can apply the virtual ground concept. If we have 1 volt here, we have 1 volt here also. And that means the potential at this point is 1 volt. Take a look at the 50 ohm resistor. It has 1 volt here and 0 volt here, which means a current will flow through it in this direction and its value will be 1 divided by 50. Let's call it I. We know current cannot flow into or out of the input terminal. That means all of I must have come through the 100 ohm resistor over here. So let us mark I here also. Now, if you take a look at this node, I must have come through these 2 branches. And they are identical. Net resistance on both branches are the same. That means I by 2 must have come through here and I by 2 must have come through here. Since I is 1 by 50, I by 2 will be 1 by 100 ampere. Let's call the potential at this point VA and the potential at this point VB. Let us also name the potential at this point Vx. Now consider this resistor 250 times 1 plus delta. It has a potential VB minus Vx across it. A current I by 2 is flowing through it. So using Ohm's law, we can write VB minus Vx is the current multiplied by the resistance. Same thing can be done with 250 times 1 minus delta also. It has a potential VA minus Vx across it. Current flowing through it is also I by 2. Using Ohm's law, we can write VA minus Vx is 1 by 100 times the resistance. What we have to find out is the value of VO. VO has to be VB minus VA. To get that, we just have to subtract this from this. Vx will just get cancelled and we will get VB minus VA. Here plus 1 and minus 1 will get cancelled and it simplifies to 1 by 100 times 250 multiplied by 2 delta. Value of delta is given in the question. It is 0.05. So we get the final output voltage, which is 250 millivolt. So that's all about it for today. See you in the next video. And please don't forget to subscribe.